Good morning, dear friends. Last class we have learned about that magnetic flux calculation and magnetic flux linkage of the toroid with the air gap, without air gap, and without the fringing effect, and with the fringing effect. Accordingly, we end up with the magnetic circuit of toroid, which has the series connection of the air gap reluctance as well as this air reluctance in the core. So then I have made a small mistake in this last class, especially in the spelling. When I explained that, let me open my whiteboard. I hope you can see the screen. In the last class, I have written it as fringing effect. The spelling mistake I made it. So actually, fringing spelling is FRINGING, fringing. So based on the fringing effect, we end up with this equation. If the core core of the material have the area width of the core is A, width of the core is A, and D is the depth of the core. So we can write area of the core, we can write it as A into D. So when we consider the fringing effect, we have to include in this area width as well as depth, adding the air gap length LG. So accordingly, in this air gap, I already told you, if we consider this fringing effect, we have to consider as air gap is greater than or equal, area of the air gap is greater than or equal, greater than area of the core. So we can write it as A can be changed as A plus length of the air gap. Similarly, depth also changed as D plus length of the air gap. So one can write it as area of the air gap can be A plus LG into D plus LG. For assumptions, usually in our calculation, simplicity of the calculation, we used to write 1.1 times of area of the core. So this is what we have learned in the last class. So last class we clearly understand what is the flux linkage, what is the reluctance of the toroid with the air gap, without air gap, and fringing, with the fringing and without fringing. In this class, we are going to learn about the mutual inductance. We are going to learn about mutual inductance. For example, we have one core like this. We have one core like this. Excuse me. Better I can use this diagram so that easily we can understand. The diagrams will be clear. So this is the core. Then inside that another one. So now we can treat it as this is the core, right? Then we have a winding. These windings are connected here. Windings are connected here. So this is the supply voltage, primary side voltage, we can write it as V1. So then secondary side also have a winding. Secondary side also have a winding. This is normally V2. So current is flowing through this primary winding. So due to this current which is flowing through this primary winding, there is a flux path in this circuit, in this magnetic core. It will be like this. So this is the flux. So for example, assume that this is the primary side and this is the secondary side, primary side, secondary side. So the secondary side is open circuit. This is the basics only what we have already learned. But anyway, this is one of the parameters we should understand very clearly for modeling of electrical machine. So open circuit in the secondary side, So if this open circuit, there is no current flow. Current flow in the circuit I2 equal to 0. We know open circuit current flow in the secondary side will be 0. So assume the flux which is produced by this produced due to the primary side coil excitation, that can be written as 511, can be written as 511. So this, it has some component, it will be leakaged through this, so that we can call it as 5L1. Then second component, that is due to the current flowing through this first winding I1, there is a flux will produced, there will be a flux will generate. This flux will linked in the secondary winding, so that we can call it as flux in the secondary winding due to the excitation in the first one. So that is what flux in the second phi 2 due to the excitation of 1. So as this secondary side is open circuited, we can write it, this total flux can be written as flux linkage in the leakage flux plus the flux linkage in the flux in the secondary winding due to the current flowing through this first winding. Then what is a flux linkage in the secondary winding? The flux linkage in the second, as this is open circuited, some flux will be linked in the linkage will be there in the secondary winding. Normally we will note it as lambda, the flux linkage. Lambda in the secondary winding is nothing but, lambda is nothing but number of, assume the number of turns in the secondary winding is N2, number of turns in the primary winding is N1. Therefore lambda is 2 is nothing but N2. Already secondary side is open, therefore number of turns in the secondary winding into the flux. Normally flux linkage lambda is nothing but N into 5. So number of turns in the secondary winding N2 into the flux linking in the secondary winding is 5 to 1. So we can write it as 5 to 1. So then voltage induced in the secondary winding, voltage is nothing but what? Voltage is in the V2 is nothing but rate of change of flux linkage with respect to time. Therefore, voltage in the secondary winding can be written as d lambda 2 by dt. D lambda 2 by dt. So the number of turns N2 is constant outside. So we can write it as 5 to 1 divided by dt. Also, we already know the basics of electric circuits and all we have learned. Lambda is equal to N into 5, right? N into 5, or otherwise we can write inductance into the current which is flowing through the circuit. So accordingly, so this here we already end up with this equation V2 equal to N2 into d 5 to 1 divided by dt. How this flux to 1 will change? When I1 is increases, flux to 1 will also increase. Similarly, I1 will decrease, automatically flux to 1 will decrease. So we can write it as phi 21 is directly proportional to the current flowing through this first winding. So when we write it as the current in the flux linkage, so we have already derived this equation, lambda 2 is equal to N2 into phi 21. So as phi 21 is directly proportional to I1, already we know this inductance will be the flux linkage in the secondary winding due to the current flowing through the front current flowing through the primary winding. So we can write this normally number mutual inductance between first and secondary winding in the current flowing through this first winding. So we can end up with this equation. Lambda 2 is nothing but N2 into phi 21 or M21 into I1. Then similarly, so therefore we can write this equation, voltage equation, take this is the equation 1. So voltage equation, induced EMF in the secondary side voltage can be written as M21 in the dI1 divided by dt. Similarly, if suppose primary is excited, secondary side is excited, if for example secondary side is excited by the current of I2 and the voltage V2, and primary side is open circuit. Primary side is open circuit. So if you write this, we goes through the same process, we can have the equation lambda 1, the flux linkage in the primary winding, can be rated as number of turns in the primary winding and flux linkages in the primary winding due to the current flowing through the secondary winding. So automatically we can write it as N1 into I2. N1 into I2. Therefore, voltage induced in the secondary. So in this side, primary side is open circuited. Primary side will be open circuited. Therefore, sorry, here one mistake. So voltage induced in this primary winding can be written as mutual inductance between the primary and secondary winding in the current flowing through the secondary winding, differentiation of current flowing through the rate of change of current flowing through the secondary winding. It's like that we can have by individually we can analyze this both the cases. Primary is excited, secondary is open. Primary is open, secondary is excited. Like that individually we can analyze this. So for some cases, if both the windings are excited, both the windings are excited, if both the windings are excited, assume, let me draw again the diagram. So now both the windings, this is primary side winding, voltage V1, current I1, then this is secondary side winding, V2, current I2. So due to the current flowing through this, there is having one leakage flux, phi L1, whatever we have learned. Similarly, due to the current flowing through this, we have a next leakage, phi L2. Then due to the current will be inducted to the secondary due to that induced EMF. So that current flux can be rated as phi in the secondary winding due to current flowing through the primary winding. Then second case, assume that these two fluxes are aiding. So I don't want to explain anything about the dot rule and all. If one can't want to learn it, can learn separately. So this is the aiding. So we can write it as phi 1 2. So flux linkage. So accordingly, how we can write in the flux in this first winding, flux in the first winding, flux in the first due to the current, flux in the primary winding, how we can write flux leakage flux in the primary winding plus induct flux in the secondary winding due to the current flowing through the primary winding plus flux in the primary winding due to the current flowing through the secondary winding. So already we know phi L1 plus phi, if we see this equation, phi L1, phi 1, we can write it as phi 1 1 plus phi 1 2. Similarly, flux in the secondary winding can be written as flux in the leakage flux plus flux in the primary winding due to the current flowing through the secondary winding plus flux in the secondary winding due to the current flowing through the primary winding. So then we can write it as phi 2 2 phi 2 2 plus phi 2 1. So this is what we have learned already. Phi 2. If you derive the secondary side is open, secondary side is excited, and primary side is open. As like this, we will get phi 2 2. Phi 2 2 is nothing but phi 1 2 plus phi 1 phi L2 plus phi 1 2. So we can write it as phi 2 2 plus phi 2 1. So now already we know. Let me erase this board. So from this we can conclude that what is a flux linkage in the primary winding? The flux linkage in the primary winding can be written as, how we can write primary winding flux linkage? Lambda 1. Flux linkage in the primary winding can be written as number of turns in the primary winding and flux in the primary winding. So if you substitute this phi 1, we can end up with N1 into phi 1 1 plus N1 into phi 1 2. Similarly, flux in the secondary winding can be written as N2 into phi 2. That can be written as N2 into phi 2 2 plus N2 into phi 2 1. So likewise, we can have this equation of lambda 1 and lambda 2. So if you substitute this, in terms of inductance, we can end up with this equation. We can end up with this equation. How lambda can be write in terms of current. So one can write it as, this is due to the self-inductance. Here also we have to concentrate the self-inductance. So these two are mutual inductance. Hence, due to the current flux in the primary winding due to secondary, here flux in the secondary due to current flowing through the primary. So accordingly, we can write in terms of inductance, lambda 1 can be written as L1 into I1 plus mutual inductance. Mutual inductance can be both the cases same. So I am writing mutual inductance M. So current flowing through I2. Similarly, lambda 2 can be rated as L2 into I2 plus mutual inductance into I1. So this is what one can write this flux linkage equation. Then finally, we can write it as, we can write this voltage equation as well. So the voltage equations can be write it as voltage in the primary winding. How we will write voltage in the primary winding? Voltage in the primary winding, V1 is nothing but d lambda 1 by dt. So accordingly, we can write L1 into di1 divided by dt plus mutual inductance into di2 divided by dt. Similarly, voltage in the secondary winding d lambda 2 divided by dt can be written as L2 into di2 divided by dt plus mutual inductance into di1 divided by dt. Then also we have already learned in this electric circuit how this we have learned in this electric circuit how that mutual relations between mutual inductance and the coefficient of coupling. So let me just I will summarize this. What are all the effects effects of this coupling? So already we know coupling effect, mutual inductance is nothing but K in the square root of L1 into L2. So from this K is nothing but M divided by square root of L1 L2. So whenever K is equal to 1, mutual inductance is nothing but self-inductance. Reason is if K is equal to 1 square root of L1 L2, if the both the windings are same, inductance are same, ideal, L1 and L2 are same, so that automatically M is nothing but inductance. So this will call it as perfect coupling. Perfect coupling. Whenever K is equal to 1, then whenever K is equal to greater than 0.5, we will call it as tight coupling. We will call it as tight coupling. Then whenever K is less than 0.5, we will call it as loose coupling. Loose to coupled circuit. So the coupling coefficient is 1 means that is perfect coupling circuit. When the coupling effect is K is greater than 0.5 means tight coupling, and whenever K is less than 0.5 means loose coupling. So this formula one can derive in our electric circuit books, whatever we have learned already. These are all the things we have learned already in our UG courses. So with this, today I would like to conclude with this. So I hope this class is very much helpful. So those who are interested to continue the forthcoming updates, kindly subscribe this channel as well as give the comment on it and give the feedback. So with these words, I would like to conclude the today's lecture, how the self-inductance, how the mutual inductance, how it is a flux linkage. So these are all the parameters very much important. One, if we want to know about that modeling of electrical machines. So wish you all the best. Thank you.